In this section, we're going to talk about limits and its relationship to continuity. As a matter of fact, we're going to define continuity based on limits. An intuitive way to think about continuity is a function is continuous if you can draw it without lifting up your pencil. That's a simple way to think about it. There are a few ways that a function can be discontinuous. First of all, the function could not be defined at a particular point C. It would have a limit at C, but it's not defined there. It could be defined there, but have no limit. Like there could be a jump and there's no limit there. Or finally, it could be defined and have a limit, but the function value, f of c, is not the same thing as a limit as x goes to c of f of x. So these three ways can be described in terms of limits and function values. In the first case, the function value is not defined. There's no function value at C1. In the second case, the limit does not exist. There's a jump there. And in the third case, the limit exists, but it's not the same as a function value. The function value is defined to be lower than the limit in this example. So this brings us to the formal definition of continuity. Now here's where in the book you'll have a little definition, and this definition is jam-packed, and so we need to take it slow to understand every definition. And we'll get more practice with this throughout the course. But we're going to start that with a function that's defined on an open interval. That means it doesn't include the endpoints, but we have an interval. And that interval has c in it. Okay, so let me draw a quick example. So the function in blue is defined over the interval in green and has c inside it. So the next part of this statement says that it's continuous at x equals c if the limit is the same as the function value. So let's check that out. At this point right there, the limit is the same as the function value. The statement goes on to say where there would be a discontinuity if the limit doesn't exist or it exists but it's not equal to f of c, the cases we talked about before. So again, if the limit exists and it's equal to the function value, it's continuous at that point c. So continuous functions behave just like you'd expect them to behave. If you add two continuous functions together, you'll get a continuous function. If you multiply a continuous function by some value k, you can multiply, and you can even divide continuous functions, and the answer is still continuous. Of course, you can't divide by 0. And most of the functions I'll be working with in this course are going to be continuous. We know that all polynomials are continuous as long as we think about their domain. So on their domain, every polynomial is continuous. Every rational function is continuous. Square roots, cube roots, nth roots are continuous, and algebraic functions that are composed of the basic operations are all continuous. Trig functions and their inverses are continuous. I may think that tangent's not continuous, but yes, tangent is not continuous over all real numbers, but it is continuous over its domain because pi over 2, for example, is not in its domain. Exponential and logarithm functions are continuous. You can even compose continuous functions. So if g is continuous at some point c, and f is continuous at g of c, then f of g of c is continuous. So just really briefly, f has to be continuous at this function value because you're going to be plugging in essentially g of c into f. So f better be continuous there. Similarly, inverse functions are continuous. If f is continuous, I'm not going to read this one. It's not going to take a big part in this chapter, but it's there if you need it in the book. Okay, in the same way that we had left and right limits, we can use the concept to have a left or a right continuous function. If you have a left limit that's the same as the function value, then it's left continuous. If you have a right hand limit that's equal to the function value at c, it's right continuous. So if we're going to sketch a function that's right continuous at 2, then we can sketch something like this. At 2, there's something which is right continuous at 2, but it's not left continuous. So it'll be like this. So we're going to be a little precise in showing that something's continuous. In practice, we'll just look at this function, for example, sine of x cubed, and just know it's continuous. But it's kind of nice to take the basic laws that we've learned and see why we can say that something like this is continuous. So let's break it down to the smaller pieces. We know that, let's call x cubed g of x. And we know that's continuous because it's a polynomial. And we were told that all polynomial functions are continuous. We know that f of x is continuous if we call f of x sine of x. Continuous because it's a trig function. And finally, we know that the composition of them is continuous because they're both continuous over their whole domain. So we're going to categorize discontinuities because some turn out to be worse than others when we're using calculus. At x equal 2, this discontinuity could be fixed if we could just change one point on the function. Like if we could redefine the function value at 2 to be the value 3, then this part of the function would be continuous. And because there was just a hole there that we could move a value and fix it, this is called a removable discontinuity. It's also removable if we would just plug a hole that didn't have a different function value there. So in the next one, the discontinuity is more drastic. There is no one point that we could fix. Like we could try plugging in a value for there, but it still would be discontinuous. So this is a discontinuity that we can't remove, and it's a jump discontinuity because the value is jumping from one point to the other eventually. So that's what it sounds like. And finally, some discontinuities are because things are going infinite positive or infinite negative, and so they're infinite discontinuities. We already talked about left and right continuous as well. Okay, we have two approaches to hit on the idea of continuity. We have one approach that uses a definition where we talk about limits, but the other approach to continuity is we've talked about functions that we know are continuous, trig functions, polynomials, and so forth. So we can actually use the fact that we know that this function is continuous on its domain if we can use that fact to find the limit. Meaning, we know this is continuous, so that means it must be that the limit of the function as x goes to some c, let's call it 2, we know that that has to be the function value. So we now have a way to calculate a limit. We can calculate the limit, we know it's continuous, so we know that the limit must be just f of c. So we plugged in 2, and we know that the limit as x goes to 2 is 1/3. This is called just substitution method. So if things are continuous, you can just substitute the value to find the limit. Now keep in mind that this is a very simplistic case, and the reason we have limits is not to deal with continuous function. We have them for other reasons. But if it happens to be easy to evaluate a limit of a continuous function, then just plug in the value and you'll get it. So let's look at all evaluating these limits. Well, these functions are all continuous on their domain. However, this last one, 2, is not in the domain because that means you'd be dividing by 0. So we can't use substitution to evaluate that limit. The other ones we can, and simply substituting in the value gives us the answer. So let's find where these rational functions are discontinuous. Well, we know they're discontinuous when the function has vertical asymptotes, so we can factor this, x plus 5, x minus 4, and find out that there are vertical asymptotes at 4 and negative 5. We know from looking at the numerator that the x-intercept at the 0 is 3, and we know that the y-intercept, if you plug in 0 for x's, is 3/20. That's pretty small. So this thing probably looks something like this. It doesn't have any more zeros, so it can't cross any of the axes. So here's what the function looks like. So these has points of discontinuity when x is equal to negative 5 and when x is equal to 4. And these are both infinite. And because they're infinite, both of these are non-removable. The situation changes, though, when we have x minus 4 in the numerator, because we can cancel this, but it still leaves a hole in the graph. This function now simplifies to a hyperbola, one that we memorized has been shifted over 5 units to the right. So this is our basic shape of the function. Boy, I'm glad we memorized this, aren't you? And so now we know that that's partly the graph, but I also have to remember that at x equals 4, there's still a hole in the graph. So I should continue this out. At this point, there's a hole. That makes a difference because it still has 2 points of discontinuity. One is removable, and x equals 4 is removable, but where x equals negative 5, it's an infinite discontinuity. I guess this also points out why it's called a removable discontinuity, because essentially we removed it by factoring and canceling the common factors. So we can look for discontinuities in other functions as well. This first one turns out to be continuous, so I'll skip that one. But the next one, the floor function, is one that you memorized, and we could you probably can figure out whether this is continuous or not. There are jump discontinuities, but we should also check whether this is left or right continuous. So in the case of a floor function, since it's continuous coming from the right, since the limits exist from the right-hand limit exists, it's right continuous. You may come across a function like this in homework. It's a pretty fun function. If you want to just type in a couple of values into a table or make a table of values, you could graph that one pretty quickly. It's a step function of sorts, and you'll see what I mean if you graph it. And let's do one final example where we prove that a function's continuous based on the bits and pieces of that function. Once again, the inside function is continuous because rational functions are continuous. Cosine is continuous because it's a trig function. And we're sticking the cosine inside another function, which is a square. This x squared is continuous, and the composition, so sticking cosine into an x squared function is another composition. We know compositions of continuous functions are continuous.